In this video, we will discuss the problem number of provinces. So the problem says that we have been given a graph which has v number of vertices in it, and we say that two vertices u and v belong to a single vertex, single province if there is a path from u to v or v to u, and our task is to find the number of provinces that are there. So a province is a group of directly or indirectly connected cities and no other city outside the group. So let us see what they are saying. So they are saying that suppose you have, let's say 1 is connected to, let's say 2, let's say 2 is connected to 3 as well. So basically you can see that from from 1 you can reach to 2, from 2 you can reach to 3. Okay, so in this area you can see that from 3 also you can reach to 2 as well as 1. So this is considered as one separate province. Okay, let's suppose there could be another province like 5, then there could be a 4, and there could be 6. So this will be considered as another separate province, because it says that a province is a group of directly or indirectly connected cities and no other city outside this group. Okay, so this is the definition of province. Like there could be just a single city also, that could be a province as well, or let's say just two cities are connected to each other like 7 and 6. If these two are connected, then they can also act as a province. Okay, so basically you can see that u is connected to v or v is connected to u. This is what the term province means. Like if I see how many provinces are there, so this is one province, this is the second province, this is the third province, and here this is the fourth province. So that is how we find the provinces. Now we will be given what? We will be given the adjacency list, like we will be given the adjacency matrix basically, and from that we have to determine that what is the number of province. So let us quickly copy the sample test case first so that we can understand this problem better. So suppose that we have been given this particular sample test case which looks like 1, then we have 0, then we have 1. Okay, so I'll make it here on the left side. So we have 1, then we have 0, then we have 1. Okay, then we have 0, then we have 1, then we have 0, then we have 1, then we have 0, then we have 1. Okay, so basically they are saying that the v is 3. So the number of nodes that are present in the graph is nothing but 3 here. Okay, suppose like if they give it like this, so basically they have given a n cross n matrix which denotes the relationship between nodes u to v. Okay, if I talk about this node, let's say if I use a 1 based indexing here, actually the indexing will be 0 based, but for now let's use a 1 based indexing. Let's say this is index number 1, this is index number 2, this is index 3, index 1. Okay, index 2, index 3. Actually the index will be 0 based, but for now we are taking it as 1. So it says that 1 is connected to 1, 2 is connected to 2, 3 is connected to 3. That is fine, but there is one other additional information given, that 1 is connected to 3. Okay, because if in the adjacency list you can see in the adjacency list of 1 and 3 is 1. Okay, so this means that 1 is connected to 3. Okay, 1 is connected to 3. Now if we see here also in the adjacency list of 3, we can see that adjacency of 3 and 1 is equal to 1. So basically that means 3 is also connected to 1. Okay, this is what they are saying. So we can observe one thing, that this is forming one connected component or one province. And if I see here, so 2 is not connected to anybody, 2 is just like this. Okay, it says that 2 comma 2 is equal to 1, so basically 2 is connected to itself, that is this. So how many provinces are there? There are exactly 2 provinces existing. Okay, there are exactly 2 provinces existing. So how can we find it? So if we see, what can we do here? So what we can basically do here is we can have a visited array. The problem is nothing but counting the number of connected components in this undirected graph. So what we will do first of all, let me take this as 0 based indexing, because actually if we are given the matrix, so it will be nothing but a 0 based index matrix. Okay, this would be the thing like this. Then what we will do is we will have a visited array. Okay, we will have a visited array in which what we will do is we'll mark all the nodes as 0. Okay, so we are having 0, 1, 2 and 3, so we'll declare a visited array of size v. Then what will happen? This is index 0, index 1, index 2. Initially we'll mark every value as 0. Okay, that is what we will do initially. Then what we will do is we will start our iteration for, like, initially we'll say that the number of province, we can say that number of province is what, number of provinces is equal to 0 initially. Okay, or we can say that our answer, or let's take it as province only. So we'll initially say that number of province is equal to 0 only. Okay, then we will start our iteration. Okay, we will start our iteration like for int I starts from 0. Okay, so we'll start from the 0th until all the nodes. Okay, so I starts from 0, I is less than n, I plus I is less than v, that is the number of nodes, the number of vertices that have been given to us, and then we do I plus plus. Okay, and if we see, is like initially we'll start from 0, so is 0 visited? No. So we will say that if visited of I, okay, if visited of I is equal to 0, then what we will do is we will call a DFS call for it. Okay, we'll simply call DFS for it. We'll say that, okay, the number of province increases by 1. We'll say that province plus plus. Okay, we'll see how it happens. So if, when we say province plus plus, then what will happen here is, if we are saying that province increases, so province becomes 1 here, right? Province will get updated to 1, and I will say now that I'll call the DFS call. I'll call the DFS call starting from this I, okay, with passing the adjacency list, passing the visited array, and passing the number of provinces, like the number of nodes in the given tree, number of vertices basically. Then what will happen if I have passed this 0? Okay, so I can see in the, if I now when I call the DFS, so first of all I'll mark it as visited. Okay, in the DFS call I'll mark this as visited, and then I will iterate. I will basically iterate for this particular current, like basically in now my current node is what, 1. Then I'll iterate in the adjacency list from 0 till v. I'll iterate and I'll check. Okay, I'll iterate from 0 to v. Basically what I will do here is I will iterate like this. Like simply what I will do in the DFS function that I have, first of all I'll mark visited of the current node as 1. Okay, then what I will do is I will iterate like for int I starts from 0, I is lesser than v, then I plus plus. Basically I'll iterate through the adjacency list. Like if there is 0, so I'll iterate like this. Here I'll iterate through this particular row of 0. I'll iterate through the row of 0 to check that with what are the vertices with which 0 is connected. Okay, that is what I would do here. So basically we'll iterate from I starts from 0, I is less than v, and then I plus plus. Okay, then what will happen, I will check that if suppose that the adjacency of the current and I is equal to 1. Okay, so is it equal to 1? And I will check that if the visited, if it is not visited, okay, if the visited of I is equal to 0, if that particular node is not visited, then I will simply call a DFS call for I comma adjacency list. I'll pass the visited array and I'll pass v here. Okay, now what will happen when I call this function here? So what basically happens, if I call it, then basically the thing that happens is, if I was at, like when I see, so actually 0 0 is 1, but it is 1, but it is already visited. Okay, because 0 is already visited, so I'll not call for it. If I see 0 1 is 0, okay, so I'll not call for it, it is not connected with me. Then if I see here, so 0 comma 2 is visited, right? So 0 is connected with 2. Basically this means that 0 is connected with 2. Basically actually 1 was connected with 3, but here since we are using 0 based indexing, actually 1 was connected with 3, but since we are using 0 based indexing, so now here 0 is connected to 3. That is what is reflected here. Okay, so now we have counted this as one province. Okay, now if I see, so I will call it and I'll mark 2 as visited. Okay, I'll mark 2 as visited, so 2 is marked as 1. Then I check in the adjacency list when I call the DFS for 2, where 2 is my current node, so I call for 2, and then I check it's all the rows. Okay, I check for all the nodes for it. So if I check, so it is 1, this is 1, 2 comma 0 is 1, but 0 is already visited, so I'll not call the DFS call for it. Then I check for 2 comma 1, it is 0, so I'll not call for it. Then 2 comma 2 is actually 1, but 2 is already visited, so I'll not call for it. Okay, then what happens, I have, like, I'll come back from that recursive call because I have counted this particular province. That is why I counted it once in this main function. I counted province plus plus, because whatever components are connected, like let's say if there was another node, let's say 5 or something, if these nodes were connected, so all the connected components will be counted as one province. Okay, so if a particular component is connected, so when we call the DFS call for it, then every node or every city present in that particular connected component will be visited, and we will count it as one province. That is why I'm doing province plus plus. Okay, then I will check. So now when I come back from the recursive calls, from the DFS calls, because there is no other thing that I can do, So I will come to this 1. When I come to 1, so I see that 1 is not visited. If 1 is not visited, then I'll call for it. Okay, I'll mark it as visited. So I'll call this 1, I'll mark it as visited, and the number of province become 2. Now I'll iterate, like in the DFS, first of all I mark it as visited. Okay, so I've marked it as visited, so I mark it as 1. Then what happens, I call for its adjacency list, right? Like I basically check in its adjacency. So this is 0, so no matter. This is 1, but actually this is already visited, right? 1 is already visited. This is 0, so actually since it is already visited, so I'll not call for it. Okay, so that means for 1 also the DFS call is over. Then after that I iterate, and I is equal to 2. So for I is equal to 2, it is already visited, so that means that I'll not iterate for it. After that what happens, my I exceeds. Okay, after that I have traversed for all the nodes and I have checked for they visited, and the number of provinces is nothing but 2. So that is how I'm counting it. Like the concept is that I use the concept of adjacency matrix here that is given to me, and that helps me to mark all the components, all the vertices that are present in the current component that are there, to mark them as visited and consider them as one single province. That is why I'm just doing province plus plus, and I'm calling for that particular component, so that all the nodes, all the vertices, all the cities present in that particular component get visited. As I said, like if suppose that there was 0, the 0 was connected to 1, like it was connected to 5, let's say it was connected to 7, so I will count it as one province. Like when I do province plus plus, I mark this as visited, this has visited, this has visited, this has visited. Okay, then what happens, it is counted as one single province. Okay, then I call for 2. So suppose 2 is connected with 3, then number of provinces counted are 2. Okay, because one province was this one, then the second province is this one. Okay, that is how we simply count. So that is how we can simply use the BFS traversal, like DFS. Basically we can use the DFS for counting the number of provinces or counting the number of connected components, you can say, in the graph. So what I will be doing here is, first of all, as I mentioned, I'll have a visited array. So I'll have a visited array, and that will be of size n, like v will be the size, that is the number of nodes. And what we will do here is, we will mark all of them as 0. Initially we'll mark all of them as not visited. Okay, 0 means not visited. Then I will say that int province is equal to 0. I'll mark initially the province as 0. Initially there is no province. Then I'll iterate through all the nodes. So I will say that I starts from 0. Okay, I is lesser than the v, and then I plus plus is what we will do. And if it happens, if the visited, right, if the visited of I is equal to 0, if a particular ith node is not visited, then I'll mark, then what I will do is, I'll say that okay, this is one such component which is not visited, and I'll first of all do province plus plus, right? So I'll do province. Okay, so I'll do province plus plus, I'll increment, like basically that is basically I'm counting the number of this as one province. Okay, and I'll call the DFS for it, so that all the nodes present in this particular connected component or present in the province gets visited. Okay, so that I do not visit them again. So what I will do is, I'll pass I, then I'll pass the adjacency list that has been given to me, adjacency matrix basically, and then I'll pass what, I'll pass the visited array. Apart from this, I'll pass the number of nodes that are there. Okay, these are the things that I would pass. And then after the recursive call, like after the calls are over, then we will have the count of the number of provinces, because we are updating it. So in the end, what we will return is, we'll return the nothing but the provinces, right? We'll return nothing but province, the number of provinces in the end. And what we will do is, we'll call a DFS function. So void DFS will call, and when we call the DFS function for ourselves, so in that particular DFS function, first of all we'll pass the current node. So that's nothing but int current node. Okay, after the current node, what we will have is, we also need to have the adjacency matrix or the adjacency list here in this case. So we'll have it like vector of vector int, okay, let's say ampersand adjacency. Then I will have another thing, that is the visited array. So int visited array is what I have. Apart from this, I have the number of nodes as v. Okay, these are the few things that I have. So once I visit a particular cell, so like visit a particular component node, I'll mark it as visited, I'll mark it as 1. Okay, indicating that it is visited. After this, what I would do is, I'll iterate, as I mentioned, I'll iterate for all the nodes in its row, in the row of the current cell, current node that I'm at. So what I will do is, I'll say that int I starts from 0, I is lesser than v as we discussed already, then I plus plus, and I'll check that if it happens that the adjacency of the current node and I is equal to 1. Okay, if they both are connected, right, if they both are connected and visited of I is equal to 0, if it is not visited, in that case what I will do is I'll simply do what, in that case maybe I can mark the visited of I as 1. Okay, or maybe I am doing it later on only. So I'll call the DFS call. Okay, and then what I will do is I'll call the DFS call for I. I'll pass the adjacency list as well. I'll pass the visited array and I'll pass v from here. Okay, then the DFS call for I will be done and it will be marked as visited as well. So that is how the code will work. Let us try and compile to see if it works on the samples. Okay, so we're getting the same output on the samples. You can see 3 is the number of components. When the test case is 0 0 0, everything is 0. So basically if there is no component that is connected, right, so in that case you will have a component 0, component 1 differently, and component 2 like they. So basically there will be 3 different provinces, right, if everything is 0 0 0. Let us try and compile this code to see if it gets accepted on the other test cases as well or not. Okay, so you can see that our solution was able to pass all the 121 test cases that are present here. And talking about the time complexity of our code, so the time complexity of our code will be nothing but order of v square, because for every node we are checking, for each and every node we are checking its row. So there are v number of, like, if there is one node, then we are checking v all the v vertices. Okay, so there are v vertices. So for them, if in the worst case we are checking v square. Okay, and since we are using a visited array, so the space complexity would be nothing but order of v. In case if you understood this explanation, so make sure to comment down understood in the chat and hit the like button as well. Thank you. In this video we will discuss the problem prerequisite tasks. The problem says that there are total n tasks. Okay, so total n tasks are there and they are labeled from 0 to n minus 1. So total number of tasks is n. They are numbered from 0 to n minus 1. So it's a 0 based index numbering. Then they are saying that some task may have prerequisites, right? So what does it mean that some particular task may have a prerequisite? So let us say that if you had to make something like Maggie. So in that case, first of all, you will do what? You will boil water. Okay, maybe you will cut some vegetables. These are the things that you will do. So that is what they are saying, that for performing some task there may be some prerequisites, as we discussed in the case of making a Maggie. So for example, to do the task 0, you have to first complete the task 1. Okay, so it says that, like, let's say they give you a relationship like this, 0, 1. Okay, if they give you a pair like this, so they are saying that to do the task 0, you first of all need to do the task 1. So basically the task 1 needs to be performed, only then the task 0 can be performed. After the task 1 has been performed, only then you can perform the task 0. Here basically they are saying that suppose there is a task A and there is a task B. So in this case they are saying that if you want to perform the task A, then B should be performed before A, such that if B is performed, B is the prerequisite task. If you perform B, then you can perform A. Okay, this is what they are saying in the problem statement. Now they are saying that you have been given the total number of tasks as n, and you have been given a list of prerequisite pairs. Okay, so basically that this particular thing, before this particular thing needs to be done. These have been given in a prerequisite array that consists of pairs. Okay, so you have to find if it is possible to finish all the tasks or not. Okay, so this problem is very interesting and it will teach us a lot. So let's quickly copy this particular sample example, the very first example that has been given to us, to check things further. So if we consider this particular case, okay, so it says that there are total 4 tasks. So task is 0, 1, 2 and 3. Fine. It says that 1, 0 is one of the pairs that has been given, then 2, 1 has been given, and then 3, 2 also has been given to us. Okay, these are the prerequisite pairs that have been basically given to us. Okay, now what we have to do is, if we observe here, so it earlier said that if 0, 1 pair is given, so that means to do the task 0, you need to perform the task 1 first of all. Okay, you need to first of all, you have to finish the task 1. You have to complete task 1. So basically, if I have to write it A, B, okay, so to do the task A, you need to first perform the task B. Okay, so let's try and build it here now. So if I have 1, 0, so that means that to do the task 1, I first of all need to do the task 0, correct? And if I have been given 2 comma 1, so that means that to perform the task 2, I first of all need to perform the task 1. Okay, to perform the task 2, to perform task 2, I first of all need to do the task 1. If I have been given 3 comma 2, so that means to perform the task 3, I first of all need to do the task 2. Okay, so basically if I extend this, so basically to perform the task 3, I need to do the task 2. Okay, now this problem is resolved. Like this problem, this is the diagram for this particular problem. But how would you resolve? Like you will say that, okay, first of all what we'll do is, we'll first of all have the 0, right? 0th that you have to think about the second case, right? Let's think about the second case, the test case that has been given to us. So second test case is like 1 0 and 0 1. Okay, so suppose if this kind of a test case has been given, like suppose 1 0 has been given and 0 1 has been given, so it says that for performing the task 1 you should have done the task 0, and this line says that for performing the task 0 you should have performed the task 1. Okay, now if you observe, if you will clearly observe, like basically this line says that to perform the task 1 you need to perform task 0. Second line says that to perform the task 0 you need to perform the task 1. So that means there is a cycle like this. Okay, here you can see one is saying that to perform the task 0 you need to perform the task 1, and to another pair is saying that to perform the task 1 you need to perform the task 0. So now there is a deadlock in between, right? Because there is a cycle that exists, right? There is a cycle that exists, and this cycle, if you remember correctly, so you must have studied this in operating systems. That's nothing but the condition of deadlocks, right? And this is also used in industries where you have to check for dependencies, right? When you're resolving some conflicts, or when you're solving some problems, right? So you need to resolve some conflicts, right? You need to see that what are the dependencies, right? So for those things we use this. The concept comes from the here only. Okay, now if you will observe this, so whenever I have a cycle, right, so I cannot, basically I cannot, this is not possible, like I cannot resolve the cycle, right? It will be a deadlock. So basically I can say that maybe what I can do is, whatever like whatever graph, like basically whatever you will be given to you, you can make a graph out of it, you can make an adjacency list out of it. Okay, how you can make the adjacency list? So you can see that basically what is happening, if I consider this 0, like 1 comma 0. Okay, if you will consider this, if I consider this case like 1 comma 0. Okay, so what is happening in the adjacency list of 0, right? In the adjacency list of 0 I'm having a 1. Okay, so that means there is an edge going towards 1. So that means that there's an in degree coming, like there's a edge coming towards 1. So that means the in degree of 1 is increasing. Okay, that is the thing. So if you will look at this diagram, so 1 comma 0, so that means that 0 is having an edge towards 1. So that means the second part of the pair is having an edge towards the first part of the pair, right? This is very, very important. Now if you will observe this, so using this way you can build the adjacency list. If you will observe, so basically in the adjacency list of 0, 1 would be there. Okay, in the adjacency list of 1, 2 would be there. In the adjacency list of 2, 3 would be there. Okay, similarly, now in this case, like basically you can say that second part, in the second part of the pair, in the second part of the pair, it's in its adjacency list, you'll have the first guy, right? First part of the pair, right? This is what you will have. Now once you have these, like once you have built the adjacency list, then it will be very easy for you to traverse and check that if there is a cycle in the graph or not. So I'm not going to discuss about how to find a cycle in a graph. Many people might be knowing that. There's something more that we can do, like there's an algorithm, that's the cadence algorithm, that's the Kahan's algorithm, sorry, that we can use, like basically that is nothing but topological sort that we can use to find that there exists a cycle or not. Okay, so what I will do is, like this particular graph has been given to me, correct? So what I can do is, I can have the in degree, right? So for implementing Kahan's algorithm, we first of all make an in degree array. Okay, so I'll make an in degree array here first of all, and then what I would do is, I'll mark the, like I'll make it like for all the values that are present here. So for 0 1 2 and 3, like the size would be n. So basically for 0 1 2 and 3 I'll get the indexes. Initially I'll mark the in degree of every node as 0. then I'll check while I'm building the graph. So if there's an edge going towards somebody, like if in this case I see 0 is making the 0 is bringing an edge, the second part of the pair is bringing an edge towards the first part of the pair, right? So basically if 0 is bringing an edge towards 1, so I'll increase the in degree of 1 by 1. Okay, so once in degree increases by 1, so once in degree becomes 1. Then if I see here, so 1 is having an edge towards 2, so that means 2's in degree increases by 1. Okay, so that means plus 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 1. Okay, then 3's in degree increases by 1 because 2 is having an edge towards 3, so that means 1 for this guy as well. Okay, that's how I've made the in degree array. Now what I will do is, whatever nodes are there that are having the in degree as 0, suppose, right, whatever nodes are there, suppose if I had a, let's say 4 also, right, if it was having if it was having an edge coming towards 4, coming towards 1, in that case what I would have done is, I would have simply stored, its in degree was also 0, I would have stored it inside the queue, but here that is not the case. So whichever, if suppose that there can be a lot of nodes that might still have the in degree as 0 here, right, so I'll insert all of them inside my queue. Okay, so here I am just having one node, so I'll insert it only, but they can happen, there can be cases where I can have a lot of nodes that have the in degree as 0. Okay, so whatever nodes are there that have the in degree as 0, I'll insert them into the queue. So first of all, I'll insert 0 into the queue. Okay, once I insert 0 into the queue, okay, so I'll run a BFS, right, I'll run a simple BFS call. And what I would do is, when I run, so initially the queue is not empty, so okay, I'll say okay, fine, so I'll take this out. When I take this out, so it basically means that I've resolved this particular conflict. Okay, and I'll mark my count as 1. I'll increase the count value by 1. Okay, I'll increase the count value by 1. Initially it is 0. Count is equal to count denotes that how many number of nodes are there, what are the total number of nodes for which the conflict has been resolved. Okay, when I have 1, okay, so now when I've removed 0, right, imagine that I've removed 0, so that means that 1 is now independent. So for that, what I will do is I'll decrease the in degree of 1 by 1. So here it becomes 0 when I decrease. Sometimes suppose there are several other edges coming towards it, so in that case the in degree can just reduce by 1, but here it is becoming 0, so it will become 0 here, right? Then what happens, I see that, okay, this, like whenever a particular guy's in degree becomes 0, I'll insert it into the queue. So I have taken out 0, then I'll insert 1 because once in degree became 0. Okay, after this there's no other there's no other guy present in the adjacency list of 0. So what I will do is, I'd simply say that now the current is 1. Okay, for 1, what I will do is, I'll iterate its adjacency list, and whatever children it has, whatever directions, whatever edges it has towards certain nodes, I'll reduce their in degree by 1. So here it is just having 2, so its in degree will reduce by 1, so it reaches 0. The moment it reaches 0, so first of all I have 2 nodes that have now become independent, like 0 and 1 both. So now the count would be 2. Okay, now 2 is inserted inside the queue because its in degree becomes 0, right? After this, what happens? After this part, what happens? If I'll observe here, so I'll take out 2. Once I take out 2, so that means 2 has also been resolved. So I'll mark the count as 3 because there are 3 nodes whose in degree has become 0. So they have been resolved, right? Their prerequisite has been fulfilled. Now when I talk about 3, so I'll iterate through the adjacency list of 2 because 2 is removed. So that means now 2 is being done, right? So that means 3 can also be done because the prerequisite for it is 2. So that means I'll decrease the in degree of 3 by 1, so it becomes 0 here. Sometimes it might not become 0 if there are the other edges coming from other nodes, right? But here it becomes 0. The moment it becomes 0, so I'll say that I'll insert 3 inside the queue as well. Then after that, I'll iterate to the adjacency list of 3. There is no node present in the adjacency list of 3. After that, what will happen? After this, 3 is also resolved, correct? So the count becomes 4 because there are 4 nodes whose dependencies have been resolved. So that means, what is the count? Now the count is equal to nothing but n, because n was 4, because we were given 4 tasks, right? 4, from ranging from 0 to n minus 1, we were given 4. So if the count becomes n, then the dependencies are resolved, and in that case we'll return what? We'll return simply true. Otherwise we'll not return true. What could be that case? So suppose if I talk about a very, very generic case, suppose the case looks something like this. Suppose I talk about a case where you have like this, where we have something like this. Okay, this kind of a conflict we have. Okay, so in this case, what will happen? You will observe that the in degree of 0, 1 and 2. Okay, so in degree of 0 is nothing but 0. In degree is the number of edges coming towards 0. In degree of 1 is nothing but 2. in degree of 2 is what? 2 as well. Okay, now when I take out 0, like you will observe that I'll push all the nodes that are the in degrees as 0 initially, like so only 0 is having the in degree as 0, I'll push it. Then that means this is resolved. If I resolve it, so whatever edges it was having towards other nodes, they will get removed. So that means once in degree would reduce by 1, so once in degree now becomes 1. Okay, then what happens if I see, does 1 in degree like, is there any node whose in degree became 0? No, currently the queue is empty. So that means I'll terminate out of the BFS because the queue became empty. And you can see that what is the count of number of nodes that for which I was able to resolve. So it is just 1, which is not equal to n here. The n is 3 here, right? So in this case, I will return a false. That's nothing but the topological sort, or you can say Kahan's algorithm, right? That's nothing but Kahan's algorithm. Okay, that is what we have to do here. So let us try and quickly write the code for it and see what we can do here. So we'll be given this particular thing. Now we have to first of all declare the adjacency list. So vector int adjacency, right? I'm declaring an adjacency list, not a vector. You can notice that I've used square brackets. Okay. Now what I've done is I would also declare in degree array. Let's say maybe I can declare it normally. So int in degree array that will be of size n, and initially all the indexes would be having the in degree as 0. Okay, then apart from this, I also need something, right? So initially, like, I will write it as pre, okay, so that I do not have much issues with it. Other than this, I will also require a q, int q. Okay, then what I will do is I'll iterate, like, for auto I is to prerequisite. When I iterate, so the first part denotes I dot first will denote the first part of the pair, I dot second will denote the second part. So what is happening if a comma b was given? So that means that if you want to do the task A, you should first of all complete the task B. So there is an edge coming from B to A. Okay, so in B's adjacency list, I would add A and I'll increase the in degree of the first part by 1 as well, right? Okay, that is what I need to do. So what I would do here is I would say that in degree of I dot first, okay, plus plus. That is the first thing that I would do. Apart from this, the other thing that I need to do is I need to put it in the adjacency list. So I'll say that adjacency of, like, adjacency of I dot second, okay, dot push back, nothing but I dot first. Okay, this is one thing that I need to do. And after we are done with this part, so what we can do is I can have a count initially that will be marked as 0, and what I would do is I would simply run, like, for int I starts from 0, I is lesser than the number of nodes that have been given to me, and then I do an I plus plus. And what I would do is if there are nodes that have the in degree as 0, so I'll push them inside the queue initially, right? So if the in degree of I is equal 0, then I'll say that simply push this I inside the queue. Okay, then what I will do is I have the count marked as 0, so I'll run until the queue size is greater than 0 or until the queue is empty, you can say. Okay, then what we will do is I'll simply say that int, like, I'll take out the current node. So current is equal to nothing but what? Current is equal to q dot front. Okay, after I've taken it out, so I'll simply pop it. Okay, that means its dependency has been resolved, and I'll do a count plus plus that, okay, this node has been resolved. Then I'll iterate through its adjacency list. So for auto, like, you can say child, okay, child is to adjacency of, like, adjacency list of the current node. Okay, then what we will do here is I'll iterate through the adjacency list of the current node, okay, through its children, and I'll mark their in degree as 0. Okay, so I'll say that in degree of the child minus minus, okay, I'll decrease the in degree by 1, and I'll check that if it happens that the in degree, okay, of the child becomes 0. Okay, so in that case what I would do is I'd simply push it inside the queue. So I'll say that q dot push the child. Okay, the child, that is basically, in terms of graph, we have a parent to child relationship now. So current node is a parent and child is the node present in its adjacency list. After I come out of this loop, so if the count of the number of nodes is equal to n, okay, in that case I will simply return a true, indicating that, okay, the dependencies are resolved. Else what I would do is I would simply return a false, okay, indicating that the prerequisites are not followed and this cannot be done, the task overall cannot be done. Now let us try and compile this code to see if it works on the samples or not, or I've made any compilation mistakes. Okay, it works on the samples perfectly. Let us try and submit this code as well. So you can see that our code was able to pass all the test cases that have been given in this particular problem. So in this problem, basically we discussed a lot. We discussed like you can find a cycle in the graph as well. In the cycle, you can build an adjacency list, find a cycle as well to detect. Or what you could do is you could simply say that you can find it using the Kahan's algorithm. Basically, that is nothing but a topological sort using the concept of in degree. So in case if you understood this problem, make sure to hit the like button and comment on understood as well. Apart from this, just a quick reminder that if you have not registered yourself for the Microsoft in 29 days self-paced course, make sure to register it. And once you register, so if you click on the start button, so you'll get access to all the days where you will be getting the recording of the 2 different problems that we do. Apart from this, the 5 problems, like basically 2 problems that we do in classwork, you'll get to solve them, and 3 problems that I gave as homework. And you'll also get the access to the leaderboard where you can check your progress amongst your peers. Thank you for watching this video.